Welcome to the lecture series on CFD, Part 2. This is Lecture 40 on solution methods for the analysis of fluid structure interaction. This lecture is devoted to solution approaches to the analysis of fluid structure interaction. First, an introduction to fluid structure interaction is given, highlighting the different solution options for steady state and transient problems. The sequential solution approach, which is suitable for steady-state fluid structure interaction problems, is outlined next, using aircraft wings as an example. Cause simulation with different codes for the computation of fluid flow and structural deformation in an explicit and an implicit version is the next topic, followed by a discussion of the optimal approach with an integrated, implicitly coupled solution approach with both solvers being part of the same code. Flowcharts of three solution approaches are described. Finally, simulation of fluid structure interaction is demonstrated on three examples: flow around a rectangular plate in crossflow, flow around a splitter plate behind a circular cylinder which can rotate, and flow in a tri-leaflet prosthetic heart valve. In Lecture 36, we studied the interaction between fluid flow and motion of a rigid body. For the body, we only solved three ordinary differential equations for linear and three for rotational motion. In many applications, the solid structure is not rigid but deformable. In that case, we need to solve momentum equations in the solid structure to determine its deformation, that is, to compute displacements and stresses. This can be done by using the following form of the momentum equation for a control volume V bounded by surface S. Here, sigma is the stress tensor and F is the resultant body force per unit volume. The stress tensor is defined via strain tensor by this equation, which can be expressed via the gradient of displacement vector by this expression. Here, mu and lambda are Lame coefficients. They are material properties of the solid. Special forms of equations are used for different solid structures, for example, for beams, plates, shells, and membranes. Forces exerted onto the structure by fluid flow affect its deformation, and the deformation of the structure affects the fluid flow. In general, there is a two-way interaction between flow and structural deformation. At the interface between solid structure and fluid, two conditions need to be satisfied. Kinematic condition, which requires that the velocities of both continua must be the same at the interface, that is, no flow through the interface. And dynamic condition, which requires that forces at the interface should be in equilibrium. Because of the two-way interaction, we cannot compute the correct deformation of the structure without knowing the forces exerted on it by fluid flow. Likewise, we cannot compute the fluid flow correctly without knowing the shape and position of the solid structure. Therefore, a coupled solution in both continua is in general required. Forces exerted onto the structure by fluid flow can lead to vortex-induced vibrations and cause serious damage to the structure if resonance occurs. The most famous example is the collapse of Tacoma Narrows Bridge in 1940 after only slightly over 4 months in operation. The bridge experienced strong oscillations in use when the wind was blowing. Professor Farquharson at the University of Washington was tasked to make wind tunnel tests and recommend solutions to reduce the oscillations of the bridge. The bridge collapsed 5 days after wind tunnel studies were finished. The two recommendations for improvement made by the investigator in his report could not be tested. Simulation of flow around deformable structures follows the same iterative solution procedure as in the case of moving rigid bodies. See Lecture 36. The difference is that the body may both move and deform, or only deform but stay fixed at one or more boundaries. The formation of a solid body is usually computed using a finite element method, although the number of researchers using the finite volume method for this purpose is increasing. In most cases, different computer codes are used to compute the fluid flow and structural deformation. These codes need to be coupled and synchronized. When a steady-state solution is sought, Simulations of flow and structural deformation can be performed sequentially. Compute fluid flow for the given shape of the structure, compute structural deformation due to computed fluid forces, and repeat until changes in flow-induced forces and structural deformation become negligible. Sequential solution of the governing equations in fluid and in solid can be optimized by using a less stringent convergence criterion at the beginning and tightening it as the changes in forces and deformations become smaller. This approach is used to study flow around airplane wings, large propeller blades, and wind turbine blades, where the shape of wings or blades changes from unloaded to fully loaded state. Usually 5 to 10 iterations, that is, solving for flow and structure in turn, are needed. Here's an example in which the sequential solution approach is suitable, determining the in-flight shape of airplane wings. The left photo shows an airplane wing on the ground. It is slightly bent down. In the right photo, the same wing is shown during flight. It is bent upwards. One needs to know the lift and drag of the wing in its deformed shape, not for the undeformed geometry. Such computations are often done using a steady-state runs approach for a constant speed without free-stream turbulence. One of the problems in studying fluid-structure interaction using different codes for fluid and structure is a different representation of the geometry, that is, different computational grids. When computing fluid flow, for example around an aircraft wing, a detailed and accurate representation of the wall surface is required. Grid is always fine at walls and the finest around wing tip, where the tip vortex is created. When computing structural deformation, an accurate surface shape is often not important. Structurally relevant solid parts are usually behind surface. For example, the internal airplane wing structure with the load-carrying frame is far more important than the skin, and the load is the lowest at the tip. Mapping loads, that is forces or stresses, from fluid to structure and deformations from structure to fluid is therefore not trivial. Sometimes the structure is simplified. For example, a 400-meter long ship may be represented by a beam with bending and torsional degrees of freedom. For the computation of flow-induced forces, no major simplification is possible. Exchange of interface data between different codes can be organized in two ways. File exchange. Each code writes data to be read by the other code into a file. Or TCP sockets, an interface between two codes, that is, a communication channel through which data can be sent and received. This is faster than writing and reading files. The first option is suitable for steady-state solutions. See slides 4 and 5. A special software for file-based co-simulation called MPCCI is marketed by the Fraunhofer Sky Institute. See their webpage for more details. The software organizes the communication between flow and structural solvers and can also map the data from one grid to the other. One code leads, the other follows. Both must have built-in provisions for data exchange and synchronization by the coupling software like MPCCI. As was the case with rigid body motion dealt with in lecture 36, coupling can be either explicit or implicit. Explicit coupling, that is, data exchange once per time step, is subject to stability constraints and is usually only effective in the case of weak interaction between fluid and structure. Implicit coupling is more robust and can be applied also to strong two-way interaction. There are two options. Data exchange after each outer iteration within a time step, that is, the structural update is part of the outer iteration loop, or multiple execution of flow and structural solution for one time step, that is, advancing to the next time step after a repeated solution for the current time step differs from the previous solution by less than a prescribed tolerance. This figure shows the flow chart of the iterative solution method in a co-simulation by two codes using explicit coupling. Flow computation always requires outer iterations, which is indicated by this loop. Structural analysis may or may not require outer iterations, depending on whether nonlinear effects are important or not. If the structural problem is linear, a direct solver can be used. If a steady-state solution is sought, very large time steps can be used with a first-order time discretization because time accuracy is then irrelevant. This figure shows the flow chart of the iterative solution method with implicit coupling of flow and structural solvers. Here, structural solution is computed iteratively as part of the auto-iteration loop, even if the problem is linear and a direct solution would be possible. For this kind of communication within auto-iterations, a more sophisticated management of interface data exchange and synchronization is needed. Usually, developers of both codes need to collaborate to make it possible. This approach works also for highly transient problems which require small time steps and second-order discretization in time. Under relaxation if both fluid and solid may need to be optimized. This figure shows the flow chart of another version of the iterative solution method with implicit coupling of two codes. This is a repetitive use of the explicit coupling shown in slide 12 within one time step. This version requires a less sophisticated communication between the two codes, but it is less efficient than the version from preceding slide. The most efficient way of coupling the solutions in fluid and in solid is to have both solvers integrated in the same code. In research communities, there are codes which use either finite volume or finite element method to compute both fluid flow and structural deformation. SimSynthesizCM+ is probably the only commercial software at the moment that includes in the same code both finite volume flow solver and finite element structural solver. Because the two solvers are part of the same code, data is directly accessed in memory. There is no need for any special communication like in co-simulation by two codes. The solution of discretized equations in both continua is integrated in the same auto-iteration loop as shown in slide 13. Interface data is updated as in the case of subdomain boundaries in parallel computing, that is, lagged by one auto-iteration. See lecture 25. Finite volume method with second-order discretization, as is typically used for fluid flow computation, is suitable only for relatively fixed solids. Arbitrary polyhedral control volumes with local grid refinement, as well as the iterative solution methods and multigrid acceleration, can then be used as for the fluid flow simulation. However, thin structures with some combination of boundary conditions require higher-order discretization. Demirjic in 2016 has shown that the fourth-order finite volume method delivers exact solution for the cantilever problem on a 4x4 control volumes grid, while second-order method produces a reasonable approximation only on a grid with 320 by 320 control volumes. Because the fourth-order finite volume discretization is more complicated than an equivalent finite element discretization, the finite element methods are usually preferred for the computation of stresses and displacements in solid structures. Let us now have a closer look at some examples of simulation of fluid structure interaction. In the first test case, we are looking at an elastic rectangular plate placed in a wind tunnel perpendicular to the air stream and fixed to the bottom along one edge. The plate is 100 mm high, 80 mm wide, and 2.5 mm thick. The density and modulus of elasticity were selected such that the first bending mode is at 4 Hz and the first twisting mode is at 20 Hz. Compressible air flowing at 10 meters per second leads to the Reynolds number based on plate width of about 50,000. Because of vortex shedding behind the plate, an unsteady runs approach was used with the k-omega SST turbulence model. Flow simulations were first performed for a rigid plate. The following results were obtained. Drag coefficient CD equal 2.1 in experiment, 2.0 in the simulation by SimSynthesizCM+. Strual number ST equals 0.156 in experiment, 0.16 in the simulation by SimSynthesizCM+. The vortex shedding frequency was 19.5 Hz, which is similar to the first twisting mode for the plate. The flow produces a very small twisting moment on the plate. A coupled simulation of flow and plate deformation was then performed using co-simulation of SimSynthesizCM+ for the flow and abacus standard for the structural deformation with implicit coupling. Because the vortex shedding frequency behind plate is close to the first twisting mode of the plate, resonance can occur. Even a small twisting moment can then cause a twisting deformation of the plate with a significant amplitude. This was happening here as shown in the animation on the right. This plot shows instantaneous distribution of von Mises stress in the plate, computed by abacus standard FE solver. Von Mises stress is a scalar variable computed from the stress tensor using this expression. It is often used to check the yield condition. The second test case was designed specifically for testing computational methods. It was also studied experimentally by Gomez and Lienhardt in 2010. A rigid steel cylinder with a diameter of 22 mm can rotate around its axis. A thin, flexible steel plate, 0.04 mm thick and 50 mm long, is attached to the cylinder. A rigid steel body, 10 mm long and 4 mm wide, is attached to the plate end as a weight. The extension in the third dimension was finite in experiments, but the problem is supposed to be two-dimensional. The structure is exposed to a laminar flow of a very viscous liquid. In experiments, a kind of syrup was used. The Reynolds number based on cylinder diameter was around 140, with mean velocity around 1 meter per second. Vortex shedding behind cylinder causes the plate to oscillate and cylinder to rotate. Simulation was performed using the integrated solution method in SimCenter software, that is, using finite volume method for the flow and finite element method for the structure, implicitly coupled in the same code. A finite extension in the third dimension was used, with symmetry conditions applied at the front and back planes. This plot shows details of the computational grid. Tetrahedral elements were used in rigid solids, hexahedral elements in the thin plate, and polyhedral control volumes with two prism layers along walls in fluid. The grid was locally refined in solid near the point where the plate is attached to the cylinder because of the expected concentration of stresses there. On the fluid side, velocities are negligible in this zone, as will be shown in slide 22, so grid refinement was not necessary. The interface between solid and fluid is non-conformal. Solution mapping by interpolation takes place at interfaces. Simulation is started with the plate behind cylinder aligned with the flow. It takes some time until vortexes on both sides of the plate develop. If the cylinder was fixed, the plate would suppress vortex shedding behind it. However, because the cylinder can rotate, small initial disturbances quickly grow, and after about 1.8 seconds, a periodic motion of cylinder and tail body is obtained. These two plots show the variation of cylinder rotation and sideways motion of the weight. The cylinder rotates by about 24 degrees on each side of its neutral position, and the tail weight moves sideways by around 20 millimeters to each side. The period of these oscillations is around 0.141 seconds. These results are close to experimental data. Experiments are affected by 3D effects because of side walls. Simulation used symmetry conditions at front and back, thus simulating an infinite body that is a 2D situation. See section 13.10.2 and the references in the book for more details about this test case. This slide shows the velocity field in fluid when the tail weight passes the middle plane on the way down, when it is at the lowest point, when it crosses the mid-plane on its way up, and when it is at the highest position. The motion of cylinder and tail body are out of phase. When the tail weight is at its lowest position, the cylinder is rotating counterclockwise, as can be deduced from the plots in preceding slide. When the tail body is at its extreme positions, that is with zero velocity, we see a small recirculation around it. The maximum velocity is about 70% higher than the mean velocity. These plots show the pressure field when the tail weight passes the midplane on the way down, when it is at the lowest point, when it passes the midplane on its way up and when it is at its highest position. This low pressure zone indicates that the cylinder is moving clockwise. Here, the wall motion is aligned with fluid motion, while here it is in the opposite direction. The Magnus effect leads to a lift force on cylinder in this direction. Here we have the opposite situation. The cylinder is rotating counterclockwise. This low pressure indicates the position of a vortex, but there is no vortex at this location, as one might expect looking at this plot. However, the unsteady streamlines have a very strong curvature here, as we can see in the vector plot. The interpretation of unsteady pressure fields around moving bodies is more difficult than in the case of steady-state flows. The last example is about the flow through a prosthetic tri-leaflet heart valve. Two simulations were performed. In one, a coupled simulation of blood flow and deformation of valve leaflets was conducted using Simpson-Testasis Plus software with finite volume method applied for the flow and finite element method for the structure. The flow was driven by a prescribed time-dependent variation of pressure at two cross-sections, one before and one after the valve. In the other simulation, the deformation of valve leaflets was performed using Simpson-Testasis Plus software and the finite element method. The deformation was driven by a prescribed time-dependent variation of pressure on the leaflet, which was derived from experimental data. In this animation, blood velocity and displacement of valve surface from its closed position are shown. The animation on the right shows the computed deformation of valve surface as it opens and closes. The computed deformations of valve leaflets are significantly different in these two simulations. These two animations show comparison of predicted heart valve opening from a coupled simulation of blood flow and valve deformation, left-hand side labeled FSI, and from simulation of valve deformation alone with a prescribed leaflet surface pressure, right-hand side denoted no FSI. Results from the FSI simulation are much more realistic. This animation shows grid adaptation to a deforming structure in two cross-sections through the fluid domain and in the visible part of one valve leaflet from a coupled simulation of blood flow and valve deformation using Simpson-Testasis Plus software. The grid in the fluid domain is morphed until its quality starts deteriorating. Then a new grid is generated. The solution from the current and from the previous time step are mapped from the old to the new grid, and the simulation is continued. This is facilitated by the use of implicit time discretization method, so that variable values from the previous time step are only needed in the time derivative. Convection and diffusion fluxes and the source terms are computed only at the new time level. This is a special kind of solution adaptive local grid refinement, driven by the variation of grid quality when it is morphed to stay adapted to deforming solution domain boundaries. More details about other options for solution adaptive grid refinement are presented in lecture 38. Here is a summary of this lecture. Forces and moments exerted by fluid flow onto solid structures can be oscillating, for example because of vortex shedding. This can lead to vortex-induced vibrations of the structure. If resonance occurs, even relatively small loads can cause large deformations and even lead to total damage to the structure, for example the collapse of Tacoma Narrows Bridge. Deformation of a solid structure also affects the fluid flow, and because of this two-way interaction, a coupled simulation of fluid flow and structural deformation is needed. The optimal approach is obtained if both solvers are part of the same code, so that interface data created by one solver, forces on walls from fluid solver, deformation of walls by structural solver, is available in memory. When two different codes are used, they need to be synchronized, and interface data must be exchanged via files or communication sockets, akin to communication in parallel computing.